Welcome back to the afternoon session. Sorry for the delay, we have had a change in the way we are projecting the lectures onto the screen. In the morning session we had looked at fluid statics, and due to problems in the projection you may have missed a few things. So, I will give a quick review and then we will move on to other things. So, we were looking at fluid statics. So, we derived the base what is called the basic equation of fluid statics. Now, some authors use the term hydrostatics instead of fluid statics. Now, strictly speaking, hydro refers to water, but the term hydrostatics is used even if the fluid is not water. So, we had this equation that 0 is equal to rho g minus grad of p. So, the first term on the right hand side is the body force per unit volume, second term is the net surface force per unit volume when the fluid is at rest. Now, a couple of days later I will be talking about inviscid flows. Where the fluid will be moving, and then you are going to have an equation of this form, rho times the acceleration is rho g minus grad p. So, the stress distribution in an inviscid fluid is similar to that in a hydrostatic fluid, and the net force and the net surface force per unit volume is still going to be minus grad p. So, what we covered today is a sort of building block for other chapters of this of our book. Now, if you look at viscous flows of a Newtonian fluid, you have rho times the acceleration, which is you can write as dv dt equal to rho g minus grad p plus mu Laplacian of v. Now, here the acceleration is related to the velocity change with respect to time. So, this is a material derivative which will be covered in kinematics. Now, what I am trying to say is that the reason I wrote all this is that the first equation is a special case of the other two. So, if you have a case when the fluid is at rest, so for a fluid at rest, your velocity at any point x, y, z any time is 0. That means the acceleration, which is dv dt, that is also equal to 0. So, if this term is 0, then this equation, which was first derived by Euler and it is called Euler's equations of motion, they reduce to the basic equation of hydrostatics. Now, this equation is referred to as the Navier-Stokes equations. Here also, if v is 0 for all x, then all spatial derivatives are 0. So, this term is 0, this term is 0, and it reduces to the basic equation of hydrostatics. So, you can view the basic equation of fluid statics as a special case of your momentum balance equations when the velocity is 0. Now, that brings us to a so in the morning session we derived the pressure distribution for a fluid with constant density. Now, suppose you have a fluid of variable density. So, now let us say rho is a function of x, y, z. Can we solve this equation grad p is equal to rho g? Now, you may or may not have a equilibrium state where the fluid is at rest when the density is varying. So, what we will do now is look at what are called the necessary conditions for a fluid to be at rest. Necessary. So, we will look at necessary condition for hydrostatic equilibrium. Now, suppose I look at this equation here, which is a vector equation. I can take the curl of both sides of this equation. So, if I take curl of the left hand side, this is given by this determinant, where in the first row you have the unit vectors I, j, k. Now, grad you can view as a vector operator I del del x plus j del del y plus k del del z. So, here in the second row we will write del del x del del y del del z. Now, grad p is a vector del p del x I plus del p del y j plus del p del z k. So, in the third row we are going to have del p del x, del p del y and del p del z. Now, if you expand this, let us do it on the carefully. Curl of grad p, I am going to write again I j k del del x del del y del del z, and here we have del p del x del p del y and del p del z. So, if we expand it and look at the I component of I here, it is given by this subdeterminant. So, we are going to have del 2 p del y del z minus del 2 p del z del y. Now, you know that if p is a continuous function and if del p del y and del p del z are continuous functions, then the order of differentiation in this mixed derivative does not matter. So, del 2 p del y del z is identically equal to del 2 p del z del y. So, this part is going to be 0. Similarly, if you look at the other terms for the j component, you are going to have del 2 p del x del z minus del 2 p del z del x. Now, again this is going to be 0, and if you look at the third component, the k component, you are going to have del 2 p del x del y minus del 2 p del y del x. So, this is also going to be 0. So, curl grad p is a vector which is going to be identically 0. Now, this you will use again when you look at potential flows, but for the timing let us go back and look at this equation, grad p equal to rho g. I have taken the curl of the right hand side and we have found that that is equal to 0. Now, if you take the curl of the right hand side, curl of rho g, this may or may not be equal to 0. Now, if curl of rho g is not 0, then there is a contradiction in the sense that when you take the curl of this equation, the curl of the left hand side is 0, but the curl of the right hand side is non 0. So, that means that hydrostatic equilibrium does not exist for such a case. So, you can a fluid can be at rest only if curl of rho g is 0. So, you have now the necessary condition for hydrostatic equilibrium is that curl of rho g must be equal to 0. Now, let us see what is curl of rho g by expanding it. This is given by this determinant I j k in the first row. Second row will be the elements of grad, which you can view as del del x, del del y and del del z, and here you are going to have rho g x, rho g y and rho g z. Now, let us say we use the coordinate system which we used in the morning with z vertically upwards and g downwards. Then we know that g is minus g k. So, this g x then is 0, g y is also 0 and g z is minus g. So, if this is minus g, then this is minus rho g. So, if you expand this, you are going to have minus g del rho del y I, and then you are going to have plus g del rho del x j, and the k part is 0 because this subdeterminant is 0. So, if curl of rho g is 0, it means that del rho del y must be 0 and del rho del x must be 0. Now, you see from this figure that the xy plane is the horizontal plane. So, the condition that has come out is that the horizontal gradient of the density must be 0. So, if density varies in the vertical direction only, then it is possible to have a hydrostatic equilibrium. So, if you have rho as a function of z, then curl of rho g will be equal to 0. Of course, here this notation is that z is vertically upwards and g is downwards. So, during the tutorial session, we will solve one problem where the density varies with the vertical coordinate, and you can find the pressure distribution by solving the basic equation of hydrostatics. Note, however, that if the density varies with x or y, then the fluid cannot be at rest. So, the body force can be balanced by pressure force only if curl of rho g is 0. So, what happens if curl of rho g is non-zero? So, let us go back to this equation. When curl of rho g is non-zero, the grad rho g term and the grad p term, they cannot cancel out. So, there will be an unbalanced force which will lead to an acceleration of the fluid. Now, we can give a physical interpretation to this also. If you consider a fluid element which is in the form of a sphere in 3D or in the form of a circle in 2D, this is the centroid. So, let us see what are the forces which act on this. One is the body force, and the body force will act at the center of gravity. Now, first we will take the case when density is constant. In this case, the weight will act at the geometric center. This is the center of gravity, the weight which is the mass of the element of fluid times gravity. Now, the other forces are the surface forces, and if the fluid is at rest, there is no shear stress, you have only normal stress. So, if I consider at this angle one area element, you are going to have a pressure which acts radially. The normal force is now in the radial direction. So, this P into dA is the force here. Now, I can take another area element here, and the force will be in this radial direction. Now, if we look at the moment about the center, since the weight is a concentrated force effectively which acts at the center of gravity, it has no moment, and all this moment of all these elemental pressure forces, that is also 0, because they all pass through this. Now, let us say rho is a function of x. We consider again the fluid element of the same shape. This is the centroid or the geometric center. Now, the center of gravity is going to be shifted horizontally because the density is varying. So, suppose the center of gravity is somewhere here, then the weight will act here. Now, if you go back here, we said the moment of this forces are 0, but the resultant need not be 0. We know that the pressure force below are larger than the pressure above, because as you go downwards in a hydrostatic fluid, the pressure increases. So, there is a net force due to pressure, and that will act at the geometric center because the moment of this elemental forces are 0. So, you have the net force due to gravity downwards and the net force due to pressure upwards. These are going to be equal, and they are going to act at the same point. Now, here let us say this is a weight, and the net force due to gravity, that will still act at the geometric center. The reason being that if you look at the moment of the elemental forces here, they are all in the radial direction and they all pass through this. So, even if this force due to pressure is equal to the weight, there is a couple which is not 0 now, because there is a distance between the point of application of the net force due to pressure and the gravity. So, such a fluid cannot be at rest. So, this is an important concept which can explain the origin of ocean currents and winds. When there is a temperature difference in the horizontal direction, it will induce a density stratification in the horizontal direction, and such a fluid will not satisfy curl of rho g equal to 0, and therefore, it cannot be at rest. All right. Now, we will look at pressure distribution in a fluid which is undergoing a rigid body motion. Pressure distribution first of all, we look at pressure distribution in a fluid which is inside a tank which is linearly accelerating. So, let us say we have a tank, this is the direction of gravity, and let us say the tank starts to move horizontally with a constant acceleration which is a. Okay. Now, it is common knowledge that under these conditions the free surface will not be horizontal. So, initially when the acceleration is 0, suppose the free surface is denoted by this dotted line, the free surface will not tilt. So, how do we find the location of the free surface? Now, we have to add the acceleration term to our equations. So, the starting point is again Newton's law, second law, mass times acceleration is the net force, and there are two kinds of forces, one is the body force and the other is the surface force. So, we can take any element of fluid inside and apply this Newton's second law to this. Now, the body force is simply mg, and the net surface force we have found in the morning session, that is minus grad p times the volume. So, anyway, for the timing let me write it this way, Fs net. Now, the mass you can get by integrating the density over the volume, or you can write it as some average density which I am calling rho star into the volume of the element. Now, to find the net surface force, in the morning session we had taken a rectangular element of fluid and found it. Now, let us do it for an arbitrary shape. So, suppose you have a fluid element of this shape and take some area element here on the surface. The orientation of the surface is described by this outward normal n. Now, if the fluid is at rest, we know that the force on this will be in the normal direction. So, you have df or dfs, the surface force is minus p n dA. So, if you want to find the net force, all you have to do is integrate this. So, Fs net is minus integral of p n dA. Now, you can use the divergence theorem and write it as minus integral of grad p into dV. Now, recall the mean value theorem in 1D. If you have integral a to b fx dx, where f is a continuous function, this is the length of the interval b minus a into the function value at some point xi, where xi lies between a and b. We do not know where it lies, but if the function is continuous, it is assured that there will exist a xi between a and b. Now, similarly, if I have a double integral, say f of x y dx dy, okay, so if this is x and y and integrating over some kind of a region R, let us say, you can write it as f of some x star y star into the area enclosed by this region. Now, x star y star will be some point inside the domain. Now, similarly, if you have a 3D case, triple integral in a 3D region, this is the region f of x y z dx dy dz, you can write it as some f of x star y star z star into the volume which is enclosed by this region. So, that way if you look at grad p dV, you can write it as grad p evaluated at some point inside the domain into the volume. So, if you go back and look at your balance equation, momentum balance equation, ma is equal to mg plus fs net, you can write it in this form. Ma equal to mg plus fs net, you can write it as rho star v into the acceleration equal to rho star v into the gravity vector minus grad p at some point into the volume. Now, if you divide by the volume, you have rho star a is equal to, and this a is also some average acceleration, rho star g minus grad p. So, it is better to write a star over here, this being the average acceleration. Now, what you can do is shrink the volume to a point. So, when you shrink the volume to the point, these average values become the local values, and you have rho times the acceleration is equal to rho g minus grad p. So, this is the equation which we have derived earlier for the case when the acceleration is 0. So, you had the basic equation of hydrostatics. Now, suppose the fluid is moving, then two things can happen. One is you can have additional stresses. So, that will be covered when viscous flows are taught. Now, if you have an inviscid fluid, or if the fluid is undergoing a motion where there is no deformation, it is behaving like a rigid body, then also shear stresses are 0, and this expression minus grad p is still valid. It gives you the net surface force per unit volume. So, what we will do now is use this equation to find the pressure distribution for the case which I indicated earlier. So, you have say water here and air above. So, when the fluid was at tank was at rest, this was the surface position of the surface. Now, the position of the surface is going to move, and you can predict the position by using this equation. So, this equation I can write as in the form grad p is equal to rho times g minus a. Now, you know from your vector calculus that if I have the level curves, suppose I say this is p of x y z is equal to some constant c1, and this is another surface p of x y z is equal to say c2, where c2 is greater than c1. Then if I take a point here, grad p is going to be normal to this, and it will point in the direction in which p is increasing. So, if you know the direction of grad p, then you can predict the shape, or to some extent locally the orientation of the surface where pressure is constant. Now, if you go back to this case, in the air the pressure is p atmosphere. So, we know that at the free surface, if you neglect surface tension effects, the pressure is going to be atmospheric pressure, which is a constant. So, grad p is going to be normal to that surface. Now, if you have a tank which is accelerating in this direction, this is your A, then minus A will be a vector which is parallel to this, but points in the opposite direction. So, if you look at minus A vector and you look at the G vector and you want to add it by the parallelogram law, then you draw this rectangle and draw this diagonal. So, this vector is going to be your minus A plus G, or G minus A. So, G minus A is a vector which is in this direction, and rho is a scalar. So, if you look at rho times G minus A, it is also going to be a vector in the same direction with a length which is rho times the length of this vector. So, we know that grad p is equal to rho times G minus A. So, grad p is in this direction. So, the surfaces of constant pressure are going to be perpendicular to this. So, if we go back to that case, this is the tank, and this was the initial level of liquid in the tank. So, initial level was horizontal when the tank was at rest. Now, the tank is moving and you have an acceleration in this direction. Now, minus A is going to be in this direction, and as I said, minus A plus G is a vector which is going to be in this direction, and rho times G minus A is going to be in the same direction, and this is the same as grad p. So, the surfaces of constant pressure are going to be perpendicular to this. So, the free surface will tilt, and of course, the volume of liquid must be conserved. So, it will have a shape somewhat like this, where this volume will be equal to this volume. So, this is the direction of grad P, which is rho times G minus A. So, here what is happening is the tank is moving and the fluid is at rest relative to the tank. So, all the fluid particles, they are at rest relative to the tank is acceleration. So, the acceleration of the fluid particles is equal to the acceleration of the tank, which is a constant. So, this A which I have written here is nothing but a constant acceleration of the tank. So, while you can see that if you have an observer who is sitting on the tank, you will see the fluid at rest. If you have an observer on the ground, you will see the fluid is moving. But although the fluid is moving, this topic you will find in most books is covered in a chapter on fluid statics. The reason is that relative to the tank, the fluid is at rest. So, this is what we may call relative hydrostatic equilibrium. Okay, so I have explained the thing using a graphical means. And now, if you want to find the pressure distribution, you look at this equation, grad P is equal to rho G minus A, and we are looking at the case where this is a constant vector. Rho also is a constant, and for us G is a constant. Now, we have seen the solution when A was 0. So, if you simply replace G by G minus A, you get the solution for the case when the fluid is undergoing a constant acceleration, constant rectilinear acceleration. So, here your pressure distribution will be rho G minus A dot R plus a constant. Or if you want to expand it, this is rho Gx minus Ax x plus Gy minus Ay y plus Gz minus Az z plus C. And if you want to find the equation of the free surface, free surface means the interface between the liquid and the air above. Equation is P equal to P atmosphere. So, you are going to have rho times Gx minus Ax x plus Gy minus Ay y plus Gz minus Az z plus C equal to P atmosphere. This is the equation of the free surface. So, you can use this to find out the equation of the free surface if you are asked to do so in a problem. Now, we will consider a case of rigid body rotation. So, we will look at a rotating fluid. So, let us say you have a cylindrical tank . So, this dashed dot line, as you know, denotes the center line, Suppose this is mounted on a turntable and we start rotating this turntable with a constant angular velocity omega. Now, suppose the water level when omega is 0 is given by this dotted line. You know that when you start to rotate it, the fluid will go down along the center line and go up. So, we will have a shape like this. So, this is the liquid and this is air above. So, we want to predict what is the shape of this when surface tension effects are negligible. Now, since the volume of the liquid is conserved, suppose the tank is tall enough, so the liquid does not spill out. In certain parts the fluid will go up, in other parts it will come down in such a way that the volume is conserved. Now, we will have to find out what is the acceleration of the fluid and then solve this equation. Rho times A is equal to rho times G minus grad of P. Now, if the fluid is rotating with a constant angular velocity, then if you take a fluid particle somewhere here, there is going to be a centripetal acceleration on this. Now, to solve this equation and find the pressure distribution, you can either use cylindrical coordinates or you have to find an expression for the acceleration in Cartesian coordinates and do it. So, suppose I have a coordinate system with the origin at this point and z upwards. So, z is upwards along the axis of this cylindrical container and the origin is here, let us say. So, this is z equal to 0. Now, if I draw the cross section of this, it is a circular tank. So, the cross section is a circle and I can show my xy axis. This is the origin. Now, if you look at a fluid particle which is somewhere here, it is moving in a circular path. So, this could also be an exercise in kinematics that given the velocity field to find the acceleration, but this is something which you have already read in your mechanics courses. So, we need not derive it right here. What we can say is that if you look at the fluid particle, the velocity will be tangent to this radial line. So, this is a swirling type of motion. Now, later on we may be using cylindrical coordinates to solve some problems. So, there is no harm in introducing cylindrical coordinates at this juncture. So, in cylindrical coordinates, I will show the view in the xy plane. If you have a point here, you draw a radial line from the origin to this point. This distance is the radial coordinate r, and the angle which this vector OP makes with the x axis is what is called theta. And if I drop a perpendicular here, you know that if I call this P prime, OP prime is your x, or and if I drop a perpendicular here, call it P double prime, then OP double prime is y. So, x is r cos theta and y is r sin theta, and z is the same as what you have in Cartesian coordinates. Now, you have unit vectors I, j, k when you use Cartesian coordinates. Here you have a unit vector E r of length 1 which is pointing radially outwards, and you have a unit vector perpendicular to that which we call E theta. Now, this angle being theta and this length being 1, you can write E r as cos theta I plus sin theta j by drawing this vector triangle. So, you can see that E r depends on theta. If you change the angle, although the magnitude is still the same, it is 1, the direction is changing. So, that you have a different vector. Similarly, if I draw the vertical line over here, this angle is theta. So, E theta is minus sin theta I plus cos theta j. So, that is also a function of the angle. So, when the fluid is undergoing a swirling type motion, pure swirl motion, your velocity vector will have only a tangential component, and you can write it in this form. The velocity vector is equal to v theta e theta. This is for pure swirling motion, and this v theta is omega r, where omega is the angular speed, which is for us it is a constant. Now, given this, you can, of course, if you want, you can express it in terms of Cartesian coordinates x y, and then you can find what is the acceleration, but you know the acceleration is going to be in the radially inward direction. So, it is going to be minus omega squared r E r. So, this is your centripetal acceleration. So, in a kinematics course, you will kinematics chapter, you will learn how to find material derivative of a function, and if you take the material derivative of the velocity, you will get this expression. So, we will not derive it here, but simply use it, and this is something I think you are all familiar with. So, this is a unit vector in the radial direction. The minus sign means that it is radially inwards. Now, you can either start with the expression for grad p in cylindrical coordinates and use this expression, or convert this to Cartesian coordinates. Now, if you go back here, we have already shown how to express E r in terms of I and j. So, if you use that, then this is minus omega square r cos theta I plus sin theta j. So, you can write A as minus omega squared r cos theta I plus r sin theta j, but we have seen that r cos theta is x and r sin theta is y. So, you can write it as minus omega squared x I plus y j. That means your A x is minus omega squared x, the x component of the acceleration. A y is minus omega squared y, this is the y component of the acceleration, and A z is 0. So, the acceleration vector I can write as A x I plus A y j plus A z k, where A x, A y, A z are what I have already written over here. Now, you go to this equation, grad p is equal to rho g minus a. Okay. For this case, your g is still minus g k, as in the previous problems we have solved. Z axis is vertical and pointing upwards, and a acceleration we have found is minus omega squared x I minus omega squared y j. So, I will first do it in Cartesian coordinates. Look at the x, y and z components of this vector equation. So, if I look at the x component, del p del x will be rho into the x component of this vector g minus a. So, that is rho g x minus a x. Now, g x is 0 and a x is minus omega squared x. So, this is rho omega squared x. Similarly, if you look at del p del y, that is going to be rho times the y component of g minus a. So, that is g y minus a y, and once again g y is 0. So, I can set this to be 0 and this is also 0, minus a y is omega squared y. So, this is rho omega squared y. Now, del p del z is going to be rho into the z component of g minus a. So, we are going to have g z minus a z. Now, here a z is 0 and g z is minus g. So, we are going to have minus rho g. So, this third equation is identical to what we have in when the fluid was at rest, but when the fluid was at rest and you can get the special case by setting omega equal to 0, these two will be 0, then this will become a total derivative dp dz is minus rho g, because if omega is 0 then del p del x and del p del y are both 0, which means p does not vary with x and y. But now there is a variation of p with x, y and z. So, there are two ways to solve this equation. So, first of all, let me start with del p del x is equal to rho omega square x. This is a partial derivative. So, if I integrate this, you are going to get p is equal to rho omega square x square by 2. Now, had it been dp dx, you would have had a constant, but this is del p del x. So, you are going to have a function now, function which does not depend on x, but it will depend on the other two coordinates. So, if you take this expression and differentiate it partially with respect to x, this term will go to 0 and this will give you rho omega square x. Now, we want to find what is this function. So, for that we have to look at the other equations. So, let us find what is del p del y. Del p del y from this equation is del f del y. Since x, y and z are independent coordinates, del del y of the first term is 0, and this we know must be rho omega squared y, that is the second equation which we have found. Now, this we can integrate with respect to y, you will get f is equal to rho omega squared y squared by 2 plus some function which you can call say f2 of z. Again, had this been a total derivative, this would have been a constant, but this is a function of y and z. So, when you are integrating partially with respect to y, this will be a function of z. If you have difficulty in understanding this, take this expression and differentiate it with respect to y to see whether you get back this. So, if you take del f del y, the first term will be rho omega square into 2 y by 2, which is rho omega square y, and the second term is going to be 0 because this is a partial derivative. So, now if I take this and substitute it back over here, you are going to have p is equal to rho omega square x squared by 2 plus rho omega squared y squared by 2 plus f2 of z. So, this function is still unknown. To find that function now, we look at del p del z. Now, if you look at del p del z, when you take these three terms and differentiate it, x, y and z are independent coordinates. So, the first two terms will go to 0 and you will get now d f2 dz, and this you know must be equal to minus rho g, that is the third equation which you have. So, this tells you that f2 of z is minus rho g z plus the constant of integration. This being a total derivative, you no longer have a function here, this is a constant. So, finally, you get p is equal to rho omega squared by 2. If you want, you can club them together, x squared plus y squared minus rho g z plus c. So, this is a, you can call it the pressure distribution in Cartesian coordinates, a function of x, y, z. Now, x square plus y square is r square. So, if you want, you can write this as rho omega squared r squared by 2 minus rho g z plus c. We have shown that x is r cos theta, y is r sin theta. So, from here, if you look at x square plus y square, you are going to have r square cos square theta plus sin square theta, which is r square into 1. So, x square plus y square is r square. So, if you have p of x y z is equal to rho omega squared by 2 into x square plus y square minus rho g z plus c, I can write it in an equivalent way. P of r and z is equal to rho omega squared by 2, instead of x square plus y square I can write r square minus rho g z plus c. So, these are two equivalent mathematical expressions which tell you how the pressure inside the rotating liquid is varying when the fluid is rotating like a rigid body. Now, this you can also get by starting with the equation in vector form and looking at the r theta z components of the vector, and that is done in many textbooks. So, I will show you how to get it in that alternative way. So, for that we will write grad p as del p del r into E r plus 1 by r del p del theta into E theta plus del p del z into E z. Now, you can look at the r theta and z components of g minus a. Now, E z is the same as k. So, you have g is equal to minus g k, which is minus g E z, and you have the acceleration vector is minus omega squared r into E r. So, if you look at g minus a, you are going to have omega squared r E r minus g E z. So, rho times g minus a you will find is rho omega squared r E r minus rho g E z, and grad p is del p del r E r plus 1 by r del p del theta E theta plus del p del z E z. Now, we will start with this equation grad p is equal to rho g minus a and equate the r theta and z components of the vector. So, if you equate the r component, you are going to get del p del r from here is equal to rho omega squared r. So, this describes the balance between the radial pressure gradient and the centripetal term, acceleration term. Now, the acceleration does not have any E theta component. So, del p del theta is 0. So, the pressure distribution is independent of theta. you can call it a rotationally symmetric solution. Similarly, if you look at the z components, you are going to have del p del z is equal to minus rho g. Now, if you want to integrate this equation here, you are going to have p equal to rho omega squared r squared by 2 plus some function of z and theta, but this second equation shows that it does not depend on z, sorry theta. So, it will be a function of z. So, if I take this equation and differentiate with respect to theta, both the terms are 0. So, second equation is satisfied, first equation is also satisfied, and to find f z we have to use the last equation. So, from here we get del p del z is df dz, which is minus rho g. That means f is minus rho g z plus some constant. So, we get the same result, p is equal to rho omega squared r square by 2 minus rho g z plus c. So, we can solve the problem either using Cartesian coordinates or using cylindrical coordinates. The Cartesian coordinates is perhaps easier, but this is what you will find in most of the textbooks. That is why I thought I should cover it. Now, I will show you a shortcut. We have seen that del p del x is rho omega squared x, del p del y is rho omega squared y, and del p del z is minus rho g. Now, if p is a function of x, y and z, then you know from your calculus that dp is del p del x dx plus del p del y dy plus del p del z dz. Now, this I can write as rho omega squared x dx plus rho omega squared y dy minus rho g dz. Now, this I can write as rho omega squared d of x squared by 2. If you look at d of x squared, that is 2x dx. So, x dx I can write as d of x squared by 2. Similarly, this one I can write rho omega squared d of y squared by 2 minus rho g dz. Now, for us rho is a constant, omega is also a constant. So, rho omega square I can pull inside this d, I can write it as d of omega rho omega squared x squared by 2. Similarly, the next term I can write as d of rho omega square y square by 2, and the last one I can write as d of minus rho g z. So, this I can combine as d of rho omega squared x squared by 2 plus rho of omega square y square by 2 minus rho g z, or in other words d of this whole thing p plus rho g z minus rho omega square by 2 x square plus y squared is equal to 0, which means that the quantity in parenthesis here is a constant. Now, this shortcut of course does not work for all cases, only when in some cases it works. In this case it works, so I thought you can quickly derive it from this. So, you have p plus rho g z minus rho omega squared by 2 x squared plus y squared is equal to a constant, which means that p is rho omega squared by 2 x squared plus y squared minus rho g z plus c. Now, if you want to do it in cylindrical coordinates also, a similar thing can be done. Then you start with this equation del p del r is rho omega squared r. Del p del theta is 0 and del p del z is equal to minus rho g. So, here we are going to view p as a function of r theta z, which means that dp will be del p del r dr plus del p del theta d theta plus del p del z dz. Or in other words, dp is rho omega squared r dr plus 0 d theta minus rho g dz. So, this I can write as rho omega squared d of r squared by 2 minus rho g dz, or since rho omega squared is a constant, I can write it as d of rho omega squared r squared by 2 minus rho g z, or in other words d of p plus rho g z minus rho omega squared r squared by 2 is 0. Hence, this quantity is going to be a constant. You are going to have p plus rho g z minus rho omega square r square by 2 is equal to some constant. Or p is equal to rho omega square r square by 2 minus rho g z plus c. Now, let us look at the equation of the free surface. So, free surface is a surface of constant pressure. So, P is equal to P atmosphere. That means you are going to have rho omega squared r squared by 2 minus rho g z plus c is equal to P atmosphere, or I can write it as rho g z is equal to c minus P atmosphere plus rho omega squared r squared by 2, or if I divide by rho g, c equal to c minus P atmosphere by rho g plus omega squared r squared by 2 g. So, this is another constant. So, this is the equation of a parabola. So, if we go back and look at this, now we have found out what is the equation which is describing this curve by finding the pressure distribution. So, we will stop here for a half an hour break, and then we will have a tutorial session.